Hi students, today we will learn one group CC disconnection, that is 1, 1 disconnection. In that we will learn about synthesis of carbonyl compounds. The easiest approach to aldehydes and ketones via 1, 1 CC disconnection is by oxidation of the corresponding alcohols. Now here you can see there is an ketone here, that's the target molecule, and we can make use of the functional group interconversion, and we can do the disconnection. So here the ketone can be converted to the alcohol group, that is nothing but alcohol on oxidation gives rise to ketone. So we're going to write down as function group interconversion FGI, and below the arrow we're going to write as oxidation. So now here from this step we can make use of the 1, 1 CC disconnection that we used for alcohol. So here we're going to disconnect the carbon which is linked to the hydroxyl group, and the bond between the carbon linked to hydroxyl group and the adjacent carbon we're going to disconnect, and hence it is called as the 1, 1 CC disconnection. Now once we disconnect, the synthons for this intermediate would be R minus and as the anion, and the cation having a positive charge on the carbon. And for this the synthetic equivalent would be the aldehyde, and also it's going to be the Grignard reagent. So these two would be the starting materials for the synthesis of the target molecule 3. Now you can further disconnect this aldehyde, that is we are going to make use of the function group interconversion. Again we can make use of the oxidation here, that is the CH2OH on oxidation gives rise to the aldehyde, right? So here on further disconnection we are going on, this can again be further disconnected, that is again we are going to make use of the alcohol disconnection, that is 1, 1 CC disconnection, and after this it is going to give rise to the formaldehyde and the Grignard reagent. So here what we can use is, this is a simple example of how we can use the ketone, we can interconvert the ketone to alcohols, and then we can do the disconnection. Now next we will also look into some more examples wherein we can directly disconnect the ketone, that will disconnect the carbonyl groups. So now these two would be the starting materials. Now using this we're going to write down the synthesis. So the synthesis would be, here we're going to make use of the PCC, that is the two starting materials on reaction with the PCC is going to give rise to the target molecule. So here everywhere we're going to make use of oxidation, and hence we are using the PCC. So this would be the normal synthesis for that particular example. The synthesis of carbonyl compounds can be obtained with oxidation of alcohols. However, there are some direct approaches to synthesize carbonyl compounds by using 1, 1 disconnection. 1, 1 disconnection of ketones gives the synthon 4, for which an ester and a Grignard reagent are used to synthesize the ketone. So now if you look at the disconnection of this carbonyl group without doing the FGI, then it would give rise to a synthon of this kind, and also it was going to give rise to the Grignard reagent. But here what happens is, as I already read here, the synthetic equivalent for this synthon would be an ester. That is, an ester would be the starting material, and it would react with the Grignard reagent to give rise to the ketone. But we know that Grignard, when the ester is slightly weaker than Grignard reagent, then Grignard reagent is going to react with the ester to give rise to a ketone, and further reaction would give rise to an alcohol. But we want to avoid the formation of alcohol because here the target molecule is a carbonyl group. So that is the meaning of this line. 1, 1 disconnection of ketones gives the synthon 4, for which an ester and a Grignard reagent are used to synthesize the ketone. But this approach is not suitable as the ketone is formed in presence of Grignard reagent and is more reactive than ester, thus alcohols would be formed. So, but what is the solution? There are two ways to overcome this problem. First one, use of a less reactive organometallic reagent which reacts with acid chloride but not with less reactive ketones. So for this, we are going to make use of organocadmium compounds, which are a very good materials for the formation of the ketones. So here, this is the general reaction wherein, see here, you can see how we are going to make use of the cadmium, and we are going to react the cadmium with the acid chloride, and it is going to generate the ketone. So this is a much better method to avoid the formation of alcohols. But whenever we want to directly disconnect the carbonyl group, then we can make use of the formation of an acid chloride as an intermediate rather than making use of ester. So this is the one solution, because as we already know that esters can react with the Grignard reagent, and Grignard reagents are more reactive than esters. Grignard reagents are more reactive than esters, and it would give rise to undesired product like alcohols. But we want to avoid that. Hence, we're going to use a different technique, that is, we're going to interconvert the synthon to an acid chloride so that it can easily react with the cadmium to give rise to the ketone. So here there's one example. The synthesis of the ant alarm pheromone, that is the target molecule 5, is used in this strategy. So here you can see how we are directly disconnecting the carbon which is attached to the carbon and the adjacent carbon, and hence we're going to name it as 1,1 CC disconnection. After disconnecting, we are going to it is going to give rise to two synthons, that is a carbonyl cation is going to be obtained, and also R minus is going to be obtained. So here what we are going to do is, the next step, the synthetic equivalent for this carbonyl cation would be the Cl minus, which is going to is the positive charge on the carbonyl carbon. So that is how we are going to get the acid chloride as an intermediate, and also the R minus, that is nothing but the Grignard reagent we are going to make use, that is RMgBr. But here the next step would be further disconnection. The further process of this acid chloride would be the step of function group interconversion. We are going to interconvert the acid chloride to the acid, carboxylic acid. That is nothing but by functional group interconversion. So now we are going to make use of the carboxylic acid as the starting material, and we can synthesize the ketone. But this would be in presence of a cadmium. So here you can see we are going to make use of dialkyl cadmium, and we are going to get the ketone. So here, whenever you have an examples of examples of carbonyl compounds, then you can always make use of this method when you can convert it to acid chloride, and then you can do the synthesis. So here you are going to the first step would be reacting with or reaction of acid chloride with thionyl chloride. See, whenever we know the reaction of acid chloride, carboxylic acid and thionyl chloride always gives rise to an acid chloride. So the first step would be reaction of the carboxylic acid with thionyl chloride, which is going to give rise to acid chloride, and this on reaction with further reaction with the organocadmium, that is here we are using diethyl cadmium. On reaction with diethyl cadmium, it is going to give rise to the ketone, that is the target molecule. So this is one approach of how we can make use of the carbonyl compounds, that is the disconnection of carbonyl compounds, and how we can write the synthesis. Now there's a second method, that is use of a reagent for 4 which does not form the ketone in presence of Grignard reagent. Nitriles are ideal as the ketone is formed only when the imine is hydrolyzed during acidic workup. The reaction between a carboxylic salt and an alkyl lithium also achieves the same result. So now here we can also make use of the nitriles. That is, we can convert the acid to the, this is for the synthesis. So you can you can do the function group interconversion of a ketone to the nitriles, and this on reaction, and that would be the starting material. Now you can use the nitriles, and on reaction with the acid chloride, on reaction with the Grignard reagent, is going to give rise to imine. Now imines are highly stable. So this can be used as an appropriate intermediate for the synthesis of the ketone. So now whenever there's a formation of imines, this on hydrolysis is going to give rise to ketone. Now here also there is not going to be any undesired products, and it is not going to give rise to any other side reaction. So here that's the reason why we can use imines as an intermediate. That's after using reacting the nitriles with the Grignard reagent is going to give rise to imine. Now this imine on hydrolysis, usually acidic hydrolysis, acid hydrolysis is going to give rise to the ketone. So this is one method. So this is a second method. Instead of using of acid chloride, you can also make use of nitriles. Now when you have examples of the carboxylic acid as starting material, then the carboxylic salts also can be used, which on reaction with the alkyl lithium is going to give rise to an intermediate, which on further hydrolysis, acid hydrolysis, is going to give rise to the ketone. So now this approach is also feasible, and also it is appropriate for the formation of the ketone. So these are some of the applications of how we can make use of the disconnection of ketones, and also these are some of the best synthesis which have been used. Now the next topic is synthesis of carboxylic acid. Direct disconnection is possible at this oxidation level, since carbon dioxide, especially convenient as solid dry ice, reacts with Grignard reagent or alkyl lithium to give a carboxylic acid. This method complements hydrolysis of cyanides, since the disconnection is the same. Now here you have an carboxylic acid. Now again we're going to make use of 1,1 CC disconnection. Now this can take place in two ways. That is, once you disconnect the bond between the carboxylic acid, that is carbon, and the adjacent carbon, and write down as 1,1 CC disconnection, it is going to give rise to two reagents, right? One is R minus, that is the synthetic equivalent would be the Grignard reagent, RMGBr, and the second would be the COOH plus, that is nothing but carboxylic acid cation synthetic equivalent would be the carbon dioxide. So this is one way of disconnecting. Now the second approach can be made use of the Ampolong cyanide, which we have already studied. So what we can do is, we can, instead of giving a positive charge on the carbon having, that is the carboxylic acid, we can give it a negative charge. That is, it is going to be COOH minus and R plus. So the synthons would be COOH minus and R plus, and for the synthetic equivalent for R plus would be an halide, which is going to attack the cation, that is R plus, and it is going to give rise to an alkyl bromide. And the second synthetic equivalent, that is for COOH minus, would be the CN minus. So this is an example of the Ampolong. We're going to make use of Ampolong here. That is the reversal of polarity, because if you look at the carboxylic acid, carbon should have had a positive charge, but we are giving a negative charge. That is called as the Ampolong process here, that we are going to make use of that, and hence we're going to get the cyanide anion is going to be obtained. Now these two can be used as the starting material. Either of the two can be used as the starting material, and it can give rise to the carboxylic acid as the target molecule. So that is nothing but, see, carbon dioxide can react with the alkyl magnesium bromide to give rise to the carboxylic salt, and here there is a COOMGBr, and this on hydrolysis, acid hydrolysis, is going to give rise to the acid. And the second method is, you're going to react the alkyl bromide in presence of cyanide anion. It is going to give rise to a nitrile group. So alkyl cyanide is going to be generated, and this on hydrolysis, acid hydrolysis, is going to give rise to acid. So these are, you can make use of both the disconnection, either A or either B disconnection. Both are correct, and you can write on the synthesis for this, which is ideal, and it is right. So this is about the CC disconnection, that is 1,1 disconnection for alcohols, carbonyl and carboxylic acid. Thank you very much.